In the last couple videos, we've talked about electric potential and electric potential energy. Now remember that potential energy is a stored energy. And when you release that stored energy, it tends to change into kinetic energy. So let's look at these parallel plates over here as an example. If you would put a charge, let's say a positive charge, over here, and push it up into that spot, now it's got electric potential energy. It's not at its resting position because it wants to follow the electric field and move this way. This is its resting position down here. Its position of no potential energy, or in the field, that would be a position of no potential, 0 volts. So we know that when you store energy in the form of potential energy, it will tend to transform into kinetic energy. Okay, so we're going to explore what happens when that transfer takes place. So we've got an example here. A charge that is moved from the top plate to the bottom plate would go through a potential difference of 100 volts. That's what you see in the diagram. What potential difference would it go through if it is only moved 5 centimeters instead of the full 10? So you've got a full 10 centimeters this entire distance in the field, and we're asking, what is the voltage difference? What's the potential difference if it only moves 5 centimeters instead of 10 centimeters? Okay, you can probably guess if this whole difference between top plate to bottom plate is 100 volts, then halfway, you'd probably guess would be 50 volts. But you'd be wrong. Just kidding, you'd be right. It totally follows logic. So if we move it half the distance, we're going to go through half the potential. Okay, so 50 volts. But we can also prove that. So we know that this field in between the two plates is uniform. The whole way it's the same. Okay, so E. That thing is the same the entire distance. We also know that the field is equal to the potential difference divided by the distance, or the separation of the plates. Now, we know that the field at 10 centimeters, so the field down here, is going to be the same as the field over here. The field at both positions is going to be the same. So we can say that E10 is equal to E5. That's not the best notation, but I'm not sure how else to write it. Okay, and so E10 is going to be the potential difference over 10 centimeters. And E5 is going to be the potential difference over 5 centimeters. Okay, but we need some subscripts over here because these are not all the same thing. So let's just call this V1, D1, V2, D2. We could call it V10 and D10. We could call it that as well, but it's not really important. What we want to show is that this 100 volts difference for 10 centimeters is going to be the same as the ratio between the 50 volt difference over 5 centimeters. Okay, but we're going to solve for that 50. So this is 0.1 meters. And remember that field strength can be measured in volts per meter. So this is hopefully making sense so far. And we're trying to solve for what's the potential difference for 5 centimeters, which is 0.05 meters. And when you multiply by 0.05, you get potential difference number 2, or the potential difference for 5 centimeters, is 50 volts. Okay, so it is a perfect ratio. If you go halfway, you're using up half the potential. If you go a third of the way, a third of the potential. Okay, so that's really just a useful piece of knowledge that you can use in problem solving. Here's our first energy transfer question. An electron has a mass of 9.11 times 10 to the negative 31 kilograms and has a velocity of 2.5 times 10 to the 4 meters per second when it enters the top of parallel plates. The potential difference of the plates is 300 volts and they're 6 centimeters apart. What is the velocity of the electron after it has moved 2 centimeters? Not the full distance, just 2 centimeters. Okay, so once this electron enters the parallel plates, at this position right over here, it will have maximum potential energy, right? And then as it moves this way, that potential energy is going to get transformed into kinetic energy. So after 2 centimeters, 1/3 of the way, it's going to have more kinetic energy than when it started, but it's going to have less electric potential energy than when it started. Okay, so we're assuming that it has a starting velocity of 2.5 times 10 to the 4 meters per second, and it's going to speed up when it enters those plates. Okay, so let's just make a list of some things that we know. First of all, we're looking for V2, and that's not voltage 2, that's velocity 2. So we're going to put an arrow on top to show that it's a vector. We know that that vector is going to be downward. Okay, so this is what we're looking for. We know the mass is 9.11 times 10 to the negative 31 kilograms. We know its initial velocity. Its initial velocity is 2.5 times 10 to the 4 meters per second. Okay, we know the total potential difference is 300 volts. We know the total separation is 0.06 meters. And we know that the distance we're actually trying to move, so we're going to call this D2, is 0.02 meters. These are all the things that we know. So we're trying to figure out, how do I use all of this stuff to get me what that final velocity is? So we can think of this two different ways. First of all, we can consider the potential energy that the electron had at the beginning, and what's the change in potential energy. Okay, that will give us the change in kinetic energy, which will tell us the change in speed, or the change in velocity. We can look at it like that. We can also think about, what is the acceleration of this charge? So there's going to be a few different strategies that you can use to figure out what that final velocity is. In our case, because this is 2 centimeters out of 6, I know that the potential difference it's going to go through is 1/3 of this total. Okay, so the potential difference we're actually going to use, change in V, is 2 out of 6, 2 centimeters out of 6 centimeters, which is 1/3 of the total. Okay, and we're going to take this 1/3 and multiply it by the 300 volts. This algebra sentence is terrible, so don't follow my example here. That equals 100 volts. So the charge, the electron, is going to go through a potential difference of 100 volts. Okay, so we know that the charge on one electron is 1 EC, and we know that it's going through 100 volts. And so that Q, 1 EC, it's negative 1 EC, that Q can help us figure out what the potential energy is, or what the change in potential energy would be. Okay, so Q, change in V. We know those two things now. We know that the charge, because it's an electron, is negative 1 EC, or 1.6 times 10 to the negative 19 coulombs. And we know that the voltage drop it's going to go through is 100 volts. Okay, and if you remember, Q times change in V is work, is change in energy. Okay, so this is equal to the change in energy, which is going to be the change in kinetic energy in this case. It's also equal to the change in electric potential energy. But that change in electric potential energy is just being transformed into kinetic energy. So we can say that this is the change in EK, because that's what we're really after. We're after how much is the kinetic energy changing. So Q times change in V is equal to EK2 minus EK1. So half mv squared, half mv2 squared, minus half mv1 squared. Now we're trying to solve for V2. Okay, this is the thing we're trying to get. And so we need to do some rearranging here. Now this is not the smoothest algebra that's ever going to be done. It's not going to be the most beautiful or elegant, but here we go. We need to add half mv1 squared to both sides. Then we need to multiply by 2. Then we need to divide by mass. Then we need to square root it. Okay, so here we go. V2 is going to be equal to the square root of Q, change in V, plus half mv1 squared. Okay, so that was that part. We also need to multiply this by 2. And we need to divide by mass. Okay, there you go. So you could, if you would like to, put the numbers in first, and then you can simplify it a little bit, and then do the algebra if that makes you more comfortable. Totally fine. Okay, so this is velocity 2. So velocity 2, I'm going to put a bunch of numbers in here and see if I can fit this in. Velocity 2 is equal to the square root of, I'm going to put this 2 in front now just because I like it better there. 2 times Q is 1.6 times 10 to the negative 19. That's coulombs. Times the voltage change, which is 100 volts, plus half times 9.11 times 10 to the negative 31 times 2.5 times 10 to the 4 squared. Okay, and all of this stuff is multiplied by 2. And we divide that by 9.11 times 10 to the negative 31. Okay, all of this is square rooted. And when you do all that, you get V2 is equal to 5.93 times 10 to the 6 meters per second. And that's down. It's a vector, so you need to have direction.